Okay, let's start today's lecture. So today we are going to learn about fuzz testing, or fuzzing in short. It is actually a very practical testing technique for finding vulnerabilities in real-world applications. So before we start, let's think about what we have learned so far. So in the second week, we actually learned functional and structural testing techniques, which are all about how can we design test inputs or test suites according to different sources of information. Like, for example, for functional testing, we are getting information from the specifications or requirements or the black box behaviors of the program. And for structural testing, we can gather information from the source code of the program to design test cases. So that's about how we design the test inputs. And then we learned about the testing target, which is determined by the different levels of testing. We can select a unit of the code as the testing target. We can also select some integrations of components of the software as our target for testing. And then we learned about different test oracles or evaluation techniques for testing. These are the utilities used for designing the test cases or doing testing in reality. And now let's learn some practical testing techniques like fuzzing here we are going to learn today. So this is like our journey so far. And this is today's outline. So like what we have learned for the general testing techniques, we can have different colors of boxes for fuzzing as well. So we can have black box fuzzing, we can have white box fuzzing, and then let's learn a new color here today, which is gray. So that's the outline. And you will be practicing gray box fuzzing in your assignment 3. So let's start with some boring definitions again. So fuzzing or fuzz testing is actually an automated testing technique that involves providing a large amount of inputs to a computer program. And then we execute the program with the large amount of inputs we have generated. And then we monitor for abnormal behaviors such as crashes, failed assertions, or even some memory leaks. So the keywords here are we are generating random data as inputs. So this is actually why it is named as fuzz testing. And then because it is a testing technique, we need to send the inputs we have generated to the program to execute. And then we monitor. So these are the 3 basic key steps of doing fuzz testing. So we generate random data, and then we execute the target with the random data, and then we monitor for errors or bugs. So based on this, so based on the definition, we can see what's the key characteristic of fuzz testing here. It is like fuzz, right? It's from the name, and you may also have heard about this fuzzy kind of thing, and the thing pops up in your mind if we talk about fuzz or fuzzy, something like this, and maybe you have on your like washing machine, you may also see this fuzzy mode. So which is like putting everything together, right, into the washing machine. So you don't care about what type of clothes you are washing, just put everything inside and then it can wash for you. So fuzz or fuzzing here actually involves, and you may also have heard about fuzzy logic in machine learning or deep learning. So fuzzy logic means that instead of like doing some actual specific quantified numbers, you are mapping these specific numbers to some like higher level of labels or categories, and this is fuzzy logic. So we are trying to like blurring things up, like removing those specific values. So this is like fuzz or fuzzy. But in the context of fuzz testing here, what we are doing is actually we are trying to create some fuzzy test inputs or some random inputs to trigger unexpected behaviors of the program. Because normally when the developers develop programs, they expect the program to accept very legit, very well formatted inputs, but they don't design the program to accept like any random inputs. So maybe there are some errors in the handling of those random inputs. So that's the basic logic of fuzz testing. So fuzz or fuzzy here in this context actually refers to the randomness nature of the input generation of fuzzing. And according to the definition of fuzzing, this is like a general workflow of fuzzing. So first, we need to create a large amount of random inputs as the test cases. So you can imagine that we can generate like, you can use some pure random logic to generate some purely random test cases, right? Or we can try to adapt some mutations, try to modify some existing test inputs to create some random inputs, right? So this is the first step. And another keyword here is that we are trying to generate a large amount of random inputs. So the amount here is actually, it actually matters here. And then we execute the target program with the inputs we have just generated automatically. As you can imagine, we can use some programs to automatically generate the test cases randomly, right? And we can also automatically use some programs to invoke the target program with the test inputs we just generated. So that's the second step. And then we observe for abnormal behaviors like crashes. So this abnormal behavior actually is determined by us. So like any unexpected behavior is considered as abnormal. And you can imagine that if we can use a dry like things like a dry sanitizer to like to compile the target, we can have like we can capture the signals from those sanitizers and make our observation more sensitive, right? So we can capture more bugs. So these are the three steps in the workflow. And because we can imagine, you can see that every step could be automated by some programs. And the program to automate this whole workflow is known as a fuzzer. So this is some key steps. And fuzzing actually is becoming a very, very practical technique for finding vulnerabilities and finding bugs in real-world systems. Actually, it's normally considered to be more powerful than unit testing, because for unit testing, you need to write the test cases manually. But for fuzzing, later we will see that we can do it fully automatically. And before we continue the journey of learning fuzzing, let's do a warm-up lab poll. So according to the workflow we just learned, which factor does not affect the performance of a fuzzer? So actually you have 4 choices if you look at this actual question here. So the first one is the execution speed of the target program. So these 3 steps are parts of the workflow. And the second option here is how do we generate the test inputs? The third option is the sensitivity about abnormal behaviors, like whether do we apply address sanitizers or not. And the last option is all the above options mattered here. So have you all finished? If you have finished, what's the answer here? What do you think is the answer? All of them. Okay, so for multiple choice questions, every time you see things like this is likely the correct answer. Most of the time, like I can't say it's 100% correct, but like 90% of the time, this one is the correct answer if you see something like this. So actually, the correct answer is all of the above actually matters for fuzzing. The first one is execution speed. Actually, it matters a lot here because we are generating random inputs to explore the different program states. So sometimes the developers, they are very actually, most of the developers, they are very careful when they design the program. So they may reject a large portion of the random inputs at the very start of the program. So if we just purely randomly generate the test cases, we cannot explore deep states inside the program. So we need to generate a large amount of this type of data to explore different program states. So in order to execute this large amount of inputs, we have to improve the speed, right? And the second one, of course, it matters because if we can generate some very useful or some very well-designed test cases, it's more likely that we are going to trigger bugs. And of course, the last one also matters because we have shown it with some demo in last week where the bugs may not be able, where we cannot actually capture the bugs if we don't use address sanitizer to compile our program, right? So all of them actually matters here for the performance. So that's all about the overview of fuzzing or fuzz testing. And let's learn about the first subfamily of fuzzing techniques, which is known as black box fuzzing. So here's a brief history of black box fuzzing. So in the early days, actually in the 1980s, people actually came up with the idea of like random testing, even earlier than this. And by that time, actually, I think if not wrong, I remember as the like C program, the C language is proposed in 1970s, something like that. And before that time, people were like writing some kind of assembly code or just code the hardware with the design of the circuits. Yeah. And by that time, actually, people started to think about how should we test the program we have programmed. And they came up with the idea of random testing in 1970s, even before like the high-level programming languages were designed. And this one was first proposed by this guy. And there were some initial efforts to evaluate the effectiveness of random testing by these two people, like Pratima and Vish Vani. And that's for hardware, but for software, it's much, much later, like almost 10 years later. So these two guys like examined the effectiveness of random testing for software in the 1980s. And the term of fuzzing came even later, like even almost 10 years, not 10 years, but like 5 years later. So it's like it was proposed by this professor here in University of Wisconsin, and it was resulted in some publications in 1990s. So the word fuzzing actually is not very, very old like other testing techniques. And black box fuzzing is like one of the earliest form of fuzzing because it's, as you can imagine from the name, it's very easy, right? We just treat the target as a black box and we don't design very sophisticated strategies inside. And the idea of why fuzzing or black box fuzzing works is actually based on the infinite monkey theorem. So this theorem is actually like this. So if we place, this is not actually a monkey, it's a chimpanzee, but let's just use this image here. So if we place a monkey in front of a keyboard, and we give this monkey an infinite amount of time to hit the keys on the keyboard, then it's almost surely that this monkey can type any text, including like complete works of William Shakespeare. So this is the infinite monkey theorem. So it's like if we have enough amount of time to continue randomly generating some data or text, we will be eventually able to get anything we want. So this is the idea. So the key here is if we have infinite amount of time, we can get anything we want, basically. So that's why in the early days, like in this engineer Steve, from the company of Apple, he developed a program called the Monkey, which is actually a random testing tool that can generate random like test cases. So to test the applications on like Mac PC. So the theory is actually tells us that if we can randomly generate a large amount of inputs, then we can eventually find some inputs that are able to trigger bugs inside the program. So that's the idea of why black box fuzzing works. However, in reality, we don't have infinite amount of time. So instead of infinite amount of time, what we always have is actually budget. So we always have budgets. We don't have infinite amount of time. We always have a limitation of time. So we need to, because we can't like run the random testing forever. So we have to think about what are the key factors affecting the performance of black box testing. So remember, these are the three key steps of doing fuzzing. So we generate a large amount of random inputs, and then we execute the target with the inputs, and we observe for normal program behaviors. So because we are the designers of the fuzzers or fuzzing technique, we cannot control the target program, right? We cannot modify the target program's behavior here because we treat it as a black box. For black box fuzzing, we cannot modify it. So we can only control the fuzzer side code. We can only modify the fuzzers we are using. So among these three factors, which ones do you think are controllable by us by modifying the code of the fuzzers? Which factors do you think are controllable by the fuzzer developers? So this one is definitely controllable, right? The test creation, because we can write. We don't need to know about like we don't need to modify the target program to design how we generate the test cases. So this is controllable by us. And actually, the execution speed is also controllable by us because there are many factors affecting the execution speed of the target program. Like, for example, a PDF parser may render different PDF files at different speed, right? We should always use like smaller PDF files as test cases to increase the speed of processing, right? So it's also controllable by us. But if we don't change the program, we are not actually able to like observe for more abnormal behaviors. So normally we cannot do that. So the two factors we can control here, actually generating program inputs and also controlling the execution speed of the target program. And for gray box fuzzing, we have more advanced techniques for improving the speed. And we will learn about that later in tomorrow's lecture. And there are several types of black box fuzzing techniques as well. So we just learned that the black box testing, we can almost only control the way of how do we generate test inputs, apart from like speeding up it, the processing time. So we can almost only do this. So the categorization of different types of black box fuzzing is based on how we generate test cases. So this is like how to generate, that's how the test cases are generated are the determining factor of different types of black box fuzzing. So the first type is mutation-based fuzzing. So which is to, rather than create a new test case from scratch, we do some mutations, or we apply some mutation operators to modify some existing inputs to create some random test cases. So this is the idea. So remember this mutation testing we have learned last week. This is different. So this is mutation-based testing, not mutation testing. So mutation testing is to mutate the target program to evaluate the quality of the test suite we created, right? But mutation-based testing or mutation-based fuzzing is actually to mutate the test inputs to create new random inputs. So the concepts are totally different. So talking about mutation-based testing, a very typical example and very new example here nowadays is that we can actually apply some perturbations to some images to like some tweaking some pixels of the image to actually disrupt the vision model to classify the picture in a totally different manner. So this is actually also known as like creating some adversarial examples for like these vision models. So this is an example of mutations we can do, and talking about doing mutations on test cases, we have to learn about a key concept, which is seed. So seed is not like the random seed you are using for those random libraries. So for random libraries, sometimes you have to like initialize the random data generator or random number generator with the seed. And that seed, normally we just use the current timestamp, right? But that is not the seed here. The seed is the program input that is used to do mutation to create new test cases. So seed is like some type of special test cases that or test inputs that we use to apply mutation operators to create new test cases. So this is called a seed. We will encounter this word a lot in today's and tomorrow's lectures. So that's the first type of black box fuzzing technique. And the second type is generation-based fuzzing. So generation-based fuzzing is about instead of using a seed, instead of like mutating or applying some modifications to the seed test input, what we do is we create test cases from scratch according to some rules. So you can see that the rules here are the key things, right? We can actually use some templates to create test cases from scratch, or we can use some models to create this, right? And one of the rules that we can use for creating new test cases is actually the context-free grammar we have learned in the previous lecture of levels of testing. So we can follow the context-free grammars specified by some grammar files to create test cases following the grammars. So this is an example of the rules for generating new test cases with generation-based fuzzing. And it is normally considered, and generation-based fuzzing is normally considered as more effective than mutation-based fuzzing because for the targets that accept structured inputs. For example, if we want to test some HTML or XML parsers, then if we just randomly mutate some existing HTML or XML files, then we are very likely to generate some illegal files. And those illegal files cannot reach the deep program states of the parser, right? So we have to follow some rules when we are generating test cases with strong structures. So that's why it is often considered more effective to use generation-based fuzzing for these type of targets. Like, for example, there are some examples of these targets, like the PDF reader, because PDF files are strongly structured, and also maybe JavaScript engine. This is the logo of the V8 engine created by Google. So for these type of targets, we better use generation-based fuzzing. However, this is considered, comparing to the mutation-based fuzzing, it is normally considered as less automated, because if we just do mutation, we can apply different mutation operators to randomly mutate the test input. But if we want to use generation-based fuzzing, we have to follow some rules, right? And you may think, okay, where do we get these rules normally, right? Actually, they are normally written by hand, so that's why it's considered as less automated than mutation-based fuzzing. So this is generation-based fuzzing. And that's all about black box fuzzing. And now let's move on to white box fuzzing. And normally white box fuzzing refers to symbolic execution. And you may have heard about this term in some other courses or in some other like materials. And this, so this concept is actually a process of building predicates and describe which execution paths will be taken and their effect on the different program states. So this is a formal definition of this symbolic execution. Again, actually, it involves 3 key steps. So it's actually white box here. So we do have the source code. And we can describe, remember, we can describe source code not only as like a piece of text. We can describe source code as different graphs, right? We can use control flow graph to describe the the source code, and we can use symbolic execution to explore the different nodes of the control flow graph in a systematic manner. And in order to explore the control flow graph, these are the 3 steps we need to do. So the first one is, because you remember this path concept of control flow graph, right? On graphs, we can have different paths. And each path is like, on a control flow graph, is an execution path of the program. It represents a trace of an execution of the target program, right? So what we do is, we need to determine the conditions which are needed for taking certain paths along the control flow graph. And we should also identify the invisible paths that can be taken, that they shouldn't. So this is a little bit abstract, but we will learn with some concrete examples later. So there are some invisible paths when we explore the program, because each new branch is actually guarded by some conditions. And if we combine conditions together, they may conflict with each other. For example, maybe at the first if, we can only enter the 2 branch when a certain number is larger than 0. But here, maybe after this branch, we require that number to be smaller than 0. Then these 2 conditions cannot be satisfied simultaneously. Then this is an invisible path. So that's the basic idea here. And the third step is that we can also try to use it to generate, because we can collect conditions on the path, and we can somehow solve the conditions. Here, given symbolic execution, we can reach target locations in the control flow graph. So this is the third characteristic here. So that's about the definition and some concepts of symbolic execution, and let's try to learn it with some examples. So symbolic execution is actually normally compared with concrete execution, or just program execution with some concrete values. So let's consider this example here. So sorry, this is not yet an example. So if we compare this symbolic execution with normal program execution, which we do every day. So normally when we execute the program on like our computer, we are doing a normal program execution. So what we do is we execute the program with actual values. However, for symbolic execution, we don't use actual values when we are executing the program like statements. So we use symbolic values. We don't put in concrete actual values inside. We will see about how this works later. So the statements, when the statements receives the value, they actually compute new values for the variables based on the concrete values. And for symbolic execution, instead of generating, because we don't have concrete values, instead of generating or calculating values, we generate new expressions that can represent a domain or a set of values. So this is the second difference. And third one is different program states can be characterized or described by different concrete values for different variables at that state. And for symbolic execution, program states are characterized by, because we don't have concrete values, we only have symbolic expressions. So it's characterized by the predicates or the combinations of different expressions that needs to be satisfied to reach that program state. So this is like a comparison between symbolic execution and program execution. And let's use a concrete example here. So let's think about this example here. So this is a very simple statement. We have 3 variables. We have mid, we have low, and high. So this statement will just like calculate the value of mid by summing up low and high and divide the sum by 2. So if we do if we execute this statement with concrete value, this is what we have. So before we run this statement, we have some concrete values for both low and high. So this symbol here is not like the power of something is just AND. So low equals, let's assume that low is assigned with the value of 8 and high is assigned with the value of 12. So the program state we have before running this statement is low equals to 8 and high equals to 12. So this is how we execute the program with concrete value. This is what happens before we run this statement. And after running this statement, the program state becomes low, because we don't modify the value of low and high here, so right? So low and high will still keep their original values. And we define a new variable here. So in this program state, we have the mid variable taking the value of 10. So this is the effect of executing the statement with concrete values. And if we execute this statement with symbolic values, this is what we are going to have. So instead of assigning like actual values to these variables, so we assign some symbols to represent the value of that variable. So before we execute this statement, we can assign low with the symbol L. So this is to denote the value of low before we execute the statement. And then we can assign a symbol H to represent the value of high, variable high. And after executing the program, instead of having this as a program state, what we have is, we know that low equals to L, high equals to H, and mid, instead of getting a concrete value, we know that it is an expression of L plus H divided by 2. So this is how we do symbolic execution. And when we take branches, it's like this. So for symbolic execution, if we take the true branch, what we do is just now, let's assume that this is a statement following our previous statement. So before that, we have this, the previous program state like this. Low equals to L, H equals to high equals to H, and mid is like the just mid value of L and H. And after taking the true branch, we will just append the true condition into the program states we're going to have. And all the program states, you can see that they are connected by AND, right? We need to satisfy all these conditions in order to take the true branch. So all these conditions must be satisfied to take the true branch. And can you imagine how taking the false branch works? Actually, before it's the same, right? But after is that we are taking the negation of the value of the true branch. So this is how we take branches using symbolic execution. So it's basically adding a constraint according to the branch we take and to the program states we have accumulated. So, and you can imagine that if we have conflicting constraints, the program states we have collected may not be always satisfiable, right? Sometimes. So that's why there could be some infeasible paths when we explore the program. And just now we learned that we can actually collect conditions and constraints when we explore the programs, when we like symbolically execute the different statements. We can accumulate like constraints and for different program states. And in order to find a solution for these constraints, we have to use something called the SMT solver. So this is basically using some math theories to calculate some satisfiable values. And we don't learn this in detail here. You just need to know that, okay, there's such a thing. We don't learn about this. This is very complex. And actually, SMT is actually a generalization of SAT, which is with some extensions to cover more data structures. So this is the difference between SAT and SMT. So SMT solvers are the tools that we are going to use for solving the constraints we have collected during the symbolic execution of the statements. And a very famous SMT solver is DAX3, which is currently maintained by Microsoft. And here is an example of solving this SMT. So let's assume that we took the false branch of the previous if statement, and these are the program constraints we need to satisfy to reach the false branch of that if statement. So what we can do is, let's take that array as example here. So we can actually assign different symbolic values to different variables, and then we add these constraints to the SMT solver, and this solver will just give us the result. So this is basically how it works. It's very simple. We just need to collect all these constraints and then add it to the solver, and the solver will automatically solve it for us. And the solution actually is either the constraints are not satisfiable, either the constraints are infeasible, or some concrete values for each symbolic value here, like the value of L, H, and mid. So it will give us this. So this is the symbolic SMT solving. So we can see that how they are matched together, right? So basically, we just initialize all the variables, and then we try to send all the constraints to the solver. So that's how we use. And unfortunately, I didn't install that Ray environment on this laptop. So you can try it out on your own laptop if you install that Ray as a dependency in Python. So it's a very large dependency. So you can try it out on your own. This program works. And this is like a typical solution that we can get. So basically, solving SMT constraints is basically finding concrete values or actual values that can satisfy the constraints. So this is like typical solution given by Z3 solver. So this is SMT solving. So as you can see, we can collect constraints, and we can calculate solutions for the constraints. So we can actually use symbolic execution to almost reach anywhere that's feasible inside the program, right? Because we can just simply accumulate the constraints, and we can try to solve the constraints. So we can basically reach anywhere. However, although symbolic execution is called execution, it is normally considered as a static analysis technique. When we learn about static and dynamic, we have learned that the key difference between static analysis and dynamic analysis is that whether we execute the program or not, right? Although symbolic execution has the word execution inside, normally pure symbolic execution is considered as static, because we don't really need to run the program on a computer. We just need to go through all the potential statements, accumulate the constraints, and use SMT solver to solve the constraints, right? So it's considered as static normally. And this is like a typical symbolic execution tree. So basically, we are just accumulating like different constraints along this on this tree, and we try to solve them. So this is how we do it. And because it's a static analysis technique, it actually fixes the problem of path explosion and program state explosion problem, because sometimes we are trying to explore all the paths of the program, but we have learned that whenever we reach a branch, the number of paths will double, right? And every time we have a loop, there is a new path, right? So in practice, in theory, we can reach almost anywhere in the program. But in reality, there are path explosion problems. We cannot fully explore the program with symbolic execution. And you can also imagine the deeper we reach inside the program, the more constraints we are going to accumulate. And sometimes we could simply collect too many constraints for the SMT solver to solve. So the solver may not be able to solve some constraints, even if the constraints are theoretically solvable, but it's just too complex. We have collected too many constraints. So there are some limitations of pure symbolic execution. We face the path explosion problem. We face the problem of some infeasible or unsolvable conditions. So that's why, and there are of course some other constraints, for example, environment interactions, because we just statically explore the program. What if the program reads from a file? If we don't execute the program, we never know like what's been read from that file, right? If we don't really execute the program. So there are some constraints that we cannot collect. So which involves the environment interactions. So what we can do is, in reality, we can combine concrete program execution paths and symbolic execution. The idea is that we can collect some concrete execution trees, and we only turn some of them, because for example, in the previous slides, we know that for program state of a concrete program execution, we have the concrete values, right? What we can do is, instead of using all concrete values or all symbolic values, we use a mixture of symbolic and concrete values. For example, we can get some concrete execution trees by using some concrete inputs of the program and having to have the trees like this. And we can try to turn this value high instead of turning both of them into symbolic values. We can only turn high into symbolic values and keep 8, the concrete value, for low. And then we can try to solve the constraints with the mixture of concrete and the symbolized values. And this technique of mixing symbolic execution and concrete execution is known as concolic execution. So this is like a more practical way of doing symbolic execution in real-world large programs. And here are some facts about symbolic execution and concolic execution, because we are not going to learn this in detail. We are not going to master this. We just need to know that there's this concept. So it's often used in automated program verification, because SMT solving is actually a very rigorous technique. It can actually provide some theoretical guarantees for the correctness of the execution results. So that's why it's often used in automated program verification rather than validation. And it's often used in some small but critical programs, like some of the smart contracts. We can use symbolic or concolic execution to explore the different program states. And it's also very popular in CDF events for symbolic execution. And it's hard to use for large real-world programs because of the issue of, I mentioned just on the previous slides, like the path explosion, like infeasible or unsolvable constraints or the environment requirement. And in my opinion, this is not really a fuzzy technique, because the idea of fuzzing is to like, you know, as indicated by the name, it's like create some fuzzy inputs, right? And symbolic execution is like we are accurately collecting some constraints, we are solving it. So it's not really fuzzing in my opinion, but people are calling this white box fuzzing. So yeah, let's just use this. So that's all about black box and white box fuzzing techniques. And before we continue, let's have a 5 minutes break. Sorry, we can't have 10 minutes, I think, because we still have a lot of content to cover today. So let's have a 5 minutes break, and I'll see you at 5 o'clock. Okay, so let's continue to the last topic today, which is gray box buzzing. So as you can see, it's a new color here. So gray. So we know that black box buzzing is like may suffer from effectiveness issues because we just treat the target as a pure black box. We may not be able to explore the um, different states of the program in a very complete manner. So this is the issue of black, and the white box having may suffer the issue of like scalability issues, just like what we discussed for the symbolic execution. We may, because we are dealing with the different program states in the source code level, we have the problems of past explosion. We have the problem of some infeasible constraints to solve. So we may have scalability issue when we apply the techniques for larger programs. So both black and white, they have their own limitations and drawbacks. So can we somehow try to combine them together to like get some better results, like black plus white? So what's coming up in your mind if you think about black and white? So this is not what we are going to have. It's not like if we combine the black and white, it's not black plus white. It's not simply like this. It's gray. So this is something in Australia, right? So we so what we want is gray box. So the key idea is so black box buzzing is not effective because we treat the target as a black box. We don't care about what's happening inside. So we are blind about what's happening inside the program. So we cannot get enough information to help us to do testing better. So that's why we have to collect some information. So the first idea is that we collect information during the execution of the program instead of like treating it purely as a black box. But unlike white box symbolic execution, we don't track every state of the program. Like for white box, we need to keep track of all the values of the variables at each program state, right? But that is too heavy. We cannot maintain that. So we only collect partial information during the program execution, which is helpful for testing. So unlike black box, we do collect information, and unlike white box, we only collect partial information. We don't collect full information. So we can still create, so this is the workflow of a typical gray box buzzing workflow. So what we do is we create a large amount of random inputs as test cases. This is the same for every fuzzing technique. And then we execute the test cases we just created. And then we observe for normal behaviors. And we also collect information here. So this is something different from black box testing. We do collect execution information. And since we have collected some information, right, we can use this information to update our strategies of doing testing. So you can see that because of the collection of this execution information, we can create a feedback loop. So we can use this feedback loop to gradually improve the performance of testing here. And talking about loop, recently there's a very famous term known as loop engineering for agents. So it's basically the same idea. For loop engineering, you run the large language model agents in like some working loop to gradually improve the performance, right? To collect feedback and improve performance. And here, this feedback loop is the same. We try to collect information and adjust our strategy dynamically. And you may wonder, okay, what kind of information do we collect and how do we use it? And that's the key of black box fuzzing. And for gray box fuzzing, in my opinion, I call it the aesthetics of violence. And let's learn about why it is, I think it's aesthetics of violence. So actually, when I was doing my PhD in Singapore, my first paper title was some kind of Fuzz, the aesthetics of violence. And I presented this paper title to my PhD supervisor. And his expression after watching the title is almost the same as in this picture here. And what he said is like, you don't look violent. And I didn't see aesthetics in this paper. So, but since now I'm graduated, and let's come back to this term again. So let's use this freely. So let me explain why I think it's aesthetics of violence. So the first keyword here is violence. Violence is about like violently cracking the target program, right? We are trying to violently cracking the target program with a large amount of random input. So we just feed the target program with a large amount of input randomly. So this is violence. So imagine this, for this form of a web page or maybe a mobile app, it's expecting us to put in names, maybe within certain lines, right? We can randomly input a very long names. We can randomly input some special characters inside, right? So this is like the idea of random. And we can try out all different things here. And the rationale is that because we have a large amount of random data, it's very likely that we can cover some unhandled or some unexpected corner cases where the developers may not have think about to handle them, so we can trigger some bugs. So we are like violently cracking the program, so that's why I'd like to use the term of violence here. But violence doesn't always work. So for example, maybe you have heard about this, like Big Bad Wolf and the Three Little Pigs, this story. So the father is like the wolf, and the pigs are like the small bugs or vulnerabilities we are trying to find. And the house is like the program. Let's use this analog here. So this is the picture of this story here. So you may know that the three different little pigs, they built three different types of houses, and they hide inside. And the wolf is trying to take down these houses to find the little pig. And some houses are like the straw and wood ones. The wolf can just break them easily, right, by blowing them up. And but for the house of brick, we cannot use violence to break into the house to find the little pig. So what we do is like in another story, it's like the little riding hood. The wolf actually pretends to be the grandma of the little girl, and then he can get in, then the wolf can get inside. So that's aesthetics. So let's learn about why, like how can we like this father be smart enough to find the bugs, to crack the house of brick. Let's learn about this. So let's assume that we have a father that can generate random strings at like any length. So we can generate a string at any length with like any content. Let's assume that we have this. And let's assume that this program takes this input string and compare it with some magic string. And if the magic string matches the input string, then the program will just crash. And let's try to find this crash. So remember, one character is 1 byte. And 1 byte is made up of 8 bits. And each bit can take the value of either 0 or 1. So if we just randomly make our guesses here, if we just randomly generate the input string, like what is the maximum number of tries to trigger the crash here? We have 2 bytes which means that we have 16 bits. So the dynamic 2 to the power of 16, right? So this is the value here. So you may think, okay, this is a very large number of tries we need to take. But actually, this is not a very big number for our computers. We can actually execute very fast enough to violently crack this program. So by trying out all the possible bytes or bits here. So this program is like the houses of straw or wood. So we can use violence to crack this program. And let's keep this assumption of this fuzzer's capability here, and let's try to think about this program. So this time, instead of comparing the whole string with like just A and B, let's compare the string character by character, and let's compare it against 5 magic bytes. So what is the maximum number of tries here to crash this program if we just randomly generate the input string? It's 2 to the power of this, yeah, it has 5, yeah. It's 2 to the power of 40, which is like a very large number here. So if you think it's still not a big number because we can still put it into the in this slide, it's actually a very large number. If we run 1,000 executions per second, this will take us almost 35 years to crack. So if we are unlucky, so this will take very long time to crack. So this is like the house of brick. We cannot violently crack this program here, as you can imagine. And normally for programs, the conditions are like much more complicated than this one here, right? This is only 5 bytes. So we cannot do this. We have to be smart. So what we can do is we add a capability to the fuzzer. So other than just generating random strings and run any less, let's assume that this fuzzer is aware of branch coverage. Let's assume that this is what we do. So once the fuzzer finds an input that can cover a new branch, like for example, if the fuzzer guesses the first byte of I'm correctly, let's tell the fuzzer that, okay, you have got I'm correct. I'm is correct. And if the fuzzer got A correctly, let's tell it, okay, A is correct. So let's assume that once this fuzzer finds a test input that can cover a new branch, it keeps that input as a seed because we are noticing it that it can cover a new branch. Remember, the key term seed is like the test input that we can use to generate new test inputs by randomly applying some mutations, right? So let's assume that we can guess the number, the bytes 1 by 1 here. And what is the maximum number of tries to crash this program this time? So let's assume that if we get I'm correctly, we keep I'm something as the input, as the seed. And then based on I'm something, we create the next test input. What's the number here? Yes, you got it correctly. It's actually 5 times 2 to the power of 8. The maximum number of tries. So it's 1,000 something. So we can see that if we just still keep the same execution speed, then this will take like almost just 1 second. So this time the fuzzer is smart enough to crack the program. So that's why I call it like aesthetics. And this is actually basically the idea of divide, somehow reflecting the idea of divide and conquer. So we are trying to gradually search through different program states. by notifying the fuzzer of the change of the states. So this is the idea here. And you may wonder, okay, how is this done? Because we know that we know that this awareness of branch coverage is giving the fuzzer some advantages of like keeping some useful seeds and keeping some useful inputs, test inputs as seeds to create new test inputs. So how do we give it this awareness? So it's done by using a technique called program instrumentation. So with this, and program instrumentation is to, as indicated by the name, is to inject some code into the original program. So we can modify the target software so we can collect some extra information like the branch coverage when the program executes. And this is like, so generally this is like, we can modify either the source code of the program, or even if the program is like already compiled, we can modify the program binary. So if we have the source code of the program, we can, if you, have you learned about compilers? Like, yeah, you learn, you know, compilation, they have RVM pass, right? So we can use RVM pass to inject logic when we do the compilation. So we will learn about some details in tomorrow's lecture about how do we do this during compilation. And we can also use some binary rewriting tools to rewrite the target program to modify its logic. And instrumentation actually enables us to profile the program because we inject extra logic, and this logic could be controlled by us. We can inject any logic inside. So the program can actually generate some information as it executes. And this is an example of how do we do the program instrumentation. So what we can do is, we know that this first, if we just try to collect branch coverage, this is what we can do. At each branch, we can inject some logic into the original program to increase some counter value, like this edge has been covered once. Because we use the plus here because this program, this whole branch might be wrapped up in a loop. So we can also count how many times we execute this branch. So inside, at the location of each branch, we can have some variables assigned to that branch to denote how many times have we executed the branch. And then after executing the program, we can collect the values of each variable here. So we know that how many times have we executed this different branches. So we can record the paths we have taken during the execution, or the branches that we have covered during the execution of the program. So this is how we collect runtime feedback using the program instrumentations. And after we can collect this, we can actually we can adjust our strategies, right? And keeping good test cases as seed for generating new test inputs is one of the strategies. It's one of the most basic strategies we can use here. We can also apply some other more advanced strategies here. And there are several strategies we can consider to update with the information we have collected. So we will learn about 3 different strategies here. So the first one is seek prioritization. And the second one is power scheduling, and the last one is test input generation. So remember, seeds are like the special test inputs that we keep in this with our father to generate new test inputs with, right? So seeds and test inputs are different. So the first strategy is seed prioritization. So it actually comes from like a very natural question when we do fuzzing. So because we have a pool of seeds, remember we can keep good test inputs as seeds to generate new ones. We have a pool of seeds. And we are generating new test inputs with a seed, right? So because we have a pool of seeds, which seed should we select next to generate new test inputs? This is the question, right? We need to decide which one to use next. And this decision process is known as seed prioritization. So we can have different strategies to do this. And this actually requires us to evaluate the quality of each seed. So we want to prioritize the usage of some more promising seeds, right? And we can define the quality of the seeds by the coverage, the code coverage of the seed. We can also consider the execution time of the seed. So for coverage, it's like the larger the better, right, for the seed. And what about execution time? Is the larger the better or the lower the better? It's the lower, yeah, good. It's actually the lower the better because we want to execute the program as fast as possible, right? So we can use different properties to evaluate the quality of the seeds. So this is like an illustration of this. So we have a pool of different seeds. And the thing is, we have this so many seeds, right? Normally we can have thousands of seeds in real world fuzzing campaigns. So we have to select which one to use next to create new test cases. And we can have some heuristics, like for example, for new coverage or deep path, several other things. Then based on these criteria or heuristics, we can select the next one to use. So this is the process of seed prioritization. And another set of strategies we need to think about is power scheduling. So power scheduling is like this. So after this decision is made after we select the seed. So after we have selected, okay, let's try to generate new test inputs with the seed. What we need to think about is how many new test inputs should we generate with the current seed, right? Like, shall we generate just one new test input? Shall we just generate 10 or 100 new test inputs, right? We need to think about this. So we need to decide the number of new test inputs after we do the seed selection or seed prioritization. So this actually requires us to evaluate the quality of the seeds again. So we can still use coverage, execution time, etc. to evaluate the quality of the seeds. And if a seed has like a better quality according to like our definition of the seed quality, then we can use it to generate more test inputs. That's the basic idea. So the basic idea is, let's assume that because CD is like reaching the deepest in this program, right? We think that, okay, CD is a better seed. Then let's just generate more test inputs with CD than the other test inputs. So this is the idea of power scheduling. So because give better seeds more chances to generate new test inputs. So this is about power scheduling. And the last type of strategy we need to think about is test input generation. So now we have selected the seed with seed prioritization. We have determined how many new test inputs to create based on the seed, right? Then we need to think about how do we actually generate the new test inputs with the current seed. And this is why we need to think about test input generation. And again, like black box or white box, like black box filing, we have two types of strategies here. We can either use mutation-based generation techniques or generation-based techniques. So, and we can also try to use some like more advanced techniques or algorithms accordingly here. Like for example, we can try out some interesting boundary values. You will be practicing this in assignment 3. You need to think about some interesting values. And we may also try to use some special values and put them into a dictionary of interesting values and use them to replace the raw content of the seed to create new test cases. So it's kind of case by case here. And gray box filing is actually considered as the most popular technique or most practical technique for finding real-world vulnerabilities nowadays. It's not only because it's like both scalable and effective. It's also because unlike like other techniques like maybe static analysis, because for static analysis you don't have the seed, right? You don't have the proof of concept to trigger the bug, right? For filing, we can keep the test input that can trigger the program and trigger the bugs. So when we submit this to the developers, we have proof. We have proof with as like the country seed. So this is like the trophy of the this is like the random size black box filer actually, but it can capture the several bugs, and you can see this is a trophy of random from its main page. You can see the latest bug, the latest CVE it found is like in 2018. This is the black box file. And CVE is like a common vulnerability exposure is maintained by the US government as a collection of different vulnerabilities in commercial or open source software. So this is a copy of Vall-nut. And you can see it almost stopped at 2018, and that's because AFL was invented kind of like in 2016. And AFL is like almost 10 years old now. It's old, but it's after the invention of AFL, you can see this is a trophy of AFL, and it's not the complete trophy of AFL. You can see it's much larger. And AFL, after the invention of AFL, people have found a lot of vulnerabilities or bugs inside some critical software infrastructures, like even the Linux kernel, or something like SQLite or like IDE, right? So these are like commonly used utilities, and people have like found a lot of vulnerabilities since the introduction of AFL. So you can see gray box filer is much more capable than black box ones from the result. And if you wonder who created AFL, it's actually a guy who worked in Google. And of course, there are several filing platforms maintained by some other companies, like the one Fuzz, which was maintained by Microsoft, if I'm not wrong. And AWS, they also provide filing services. So it's like used by a lot of large companies nowadays. And we will learn about the details of AFL in the next lecture tomorrow. And that's all for today's content. And before we end our lecture, let's quickly go through what we have learned to make sure that you can remember the key concepts. Go to the overview page. So today we have learned about a very practical testing, automated software testing technique, which is known as Fuzz testing or fuzzing. And as indicated by the name, it's all about creating fuzzy test inputs, right? And fuzzy test inputs is random inputs. So the key idea of fuzzing is to create a large amount of random inputs and feed it to the target program and observe for abnormal behaviors. And it can find bugs because this large amount of input can almost guarantee to get whatever we want, right, according to the infinite monkey theorem. So, and also because it is random, we can also try to trigger some unexpected behaviors, which the programmers may not have thought about when they designed the program. And for fuzzing, there are 3 different types of fuzzing according to how much information do we know about the internals of the target program. If we don't care about what's happening inside the program, then it is black box fuzzing. Because for black box fuzzing, we can almost only control the inputs we generate and maybe the execution speed. But the execution speed is also controlled by the inputs we generated, right? So therefore, we can categorize the black box fuzzing techniques according to how we generate the inputs. Like we can use mutation-based generation, and we can also use generation-based fuzzing, right? For mutation-based, we are mutating some seed inputs. For generation-based, we can generate according to some templates or some rules, right? And if we collect every piece of information, like during the program execution, then we are doing white box fuzzing, and white box fuzzing is often considered as doing symbolic execution. And symbolic execution is all about collecting different constraints along the way of executing the program, like different statements. And once we have collected the constraints, we can use SMT solvers to solve the constraints and get some concrete values to reach certain location in the program. And because this is because we are trying to accumulate different constraints, we may suffer the issue of like scalability, right? Because there are problems of path explosion, there are problems of like unsolvable constraints, there are problems of the uncertainty of the interaction with the execution environment, right? So symbolic execution is often considered as not very scalable. And to mitigate that, we can do concurrent execution, but it's still not very scalable. So black box and white box fuzzing techniques, they all have their drawbacks. So why don't we combine them together and create gray box fuzzing? So the key idea of gray box fuzzing is that we still collect information, but we only collect the information that's needed for doing testing. And the key workflow of doing gray box fuzzing is that we create a large amount of inputs, and then we execute the program with the inputs. And during the execution, apart from the abnormal behaviors, we also try to collect execution information and use the collected information to keep new seeds, to adjust the seed prioritization, to adjust our scheduling, and to guide the new seed generation, new test input generation. So we can use the runtime information to adjust our strategy to make it more adaptive. So that's gray box fuzzing. And the key idea of keeping new seed is like reflecting the concept of divide and conquer, because we are trying to divide the exploration of the program states according to the seeds we keep. So that's all for today's lecture, and thank you for coming, and see you tomorrow. Thank you.